Right, so I'm going to talk to you about a new semantics that we have built for C and C++ type languages. It's a semantics that deals with weak memory concurrency. So first, I'm just going to give a quick primer on what weak memory concurrency is. A lot of people will probably have seen this before. I have to say my animations are not working through this mode, so that hopefully will be all right, but where it isn't, hopefully you'll bear with me. All right, so for starters, let's take a little program here. So this is the code under thread 1 and thread 2. And we're going to talk about how that executes, what behaviors are allowed by the program. So each thread contains a load from a variable. So on the left-hand thread, thread 1, it's a load of x, and it stores it into a register on thread 1, R1. And that register is then, the value of that register is written back to a variable y, and that's a sort of shared variable that other threads can execute. Thread 2 reads from y, puts it into a register, and then writes the concrete value 42 back to x. The question is, what kind of behaviors are allowed from this program? Oh, I should say one more thing, which is that in this program, there is an initialization of all variables to 0 before these two threads execute. So in sequential consistency, all of your threads, you can model that as all of your threads being interleaved, and each access of memory taking immediate effect in a global memory. So the outcome in particular of reading 42 in x and y is forbidden, because that looks like essentially a kind of reading from the future on one thread or the other. Sequential consistency disallows that. So the point about weak memory is to allow for some of these little concurrent tests, we call these litmus tests, for some of these litmus tests to allow some behavior that sequential consistency doesn't allow. So for this example, we're going to think about that 42 behavior. And if we're allowed to, for instance, reorder the load of y and the store of x on thread 2, then the behavior reading R1 and R2 42 is suddenly allowed. And the question is, why would we want to do that? The answer is that some processor architectures that we'll compile our C and C++-like languages down to will permit this kind of behavior, where there's a reordering on one thread leading to non-sequentially consistent outcome for this test. And the compiler might choose to reorder the load of x and the load of y and the store of x as well. So on this slide, there's a little yellow arrow on thread 1, and that's to highlight that there's a difference between the two threads. So on thread 2, we've got this absolute right of 42. It's like a concrete value. So the compiler doesn't need any more information than what's in the single line of code to send off that right of x. It knows it's going to be a right of 42. On thread 1, it has to wait for the value of R1 to come in from the load. So on the left-hand side, there's a dependency between the load and the store. And on the right-hand thread, there's no dependency. That's going to be something we talk about quite a bit as this talk unfolds. So here I'm just showing you the reordering. So specifications like C++, C, OpenCL, Linux, ARM, and NVIDIA, and even others, are based on axiomatic models. So these are mathematical models that tell you how the behavior of the system should be in a general sense. So the model won't tell you the specific behavior that you'll observe on a particular ARM processor, but it'll tell you what's allowed by the architecture. And similarly for C++, it's what the language would allow, but in practice you should observe no more behavior than that, but maybe quite a bit less. We've got to allow in the language this behavior of 42 in order to compile it directly to loads and stores on the processor architectures where that behavior is still allowed. And the way an axiomatic model will explain that, I should say an axiomatic model, it treats the program, it semantics the program by listing a number of possible executions. Executions are graphs of memory accesses, where each graph corresponds to like one path of control flow and one choice of read values. It then applies, it builds relationships between those events. So that might be program order. On the right, you have an execution, I should say. And the blue arrows there are program order. the green arrows are reads from, so this tells you where a particular read gets its value from. Now, given a graph with some choice of program order and reads from, the axiomatic model will constrain whether that graph, that particular behavior of the program, is allowed or forbidden. And it'll do that with rules like saying program order union RF must be acyclic. So that's a rule which is typical in C++, in the C++ specifications we use in academia, because without it, it's very difficult to work with these models. The problem is that that restriction is too strong. So if we look at that program on the left with thread 1 and thread 3, here we have register R1 linking the load of X to the store of Y on thread 1, and register R2, which carries the value from the load of Y to the store of X on thread 3. Should we be allowed to observe 42? The answer is no, this makes no sense. There's no concrete right of 42 in the program. We call this an out of thin air execution if we were to observe 42. And this should be forbidden by the processor vendors. It is forbidden by the processor vendors. It should be forbidden in the programming language. And some C++ models allow it for reasons we'll get onto, and some C++ models forbid it because without this restriction, it's very difficult to reason about the model. This turns out to be a really major problem and an open problem in the programming language definition of C++ in particular. And the International Standards Organization is interested in that. It's looking at academia for some solutions. So why don't we just allow, let's see. I'm just going to give you essentially another test which explores the problem a little bit. There's one possible solution, which is we just spot when these dependencies arise. In that program I showed you before, there's an obvious syntactic dependency from the load of Y to the store of X. Here on the right-hand side, I've drawn that dependency in orange. The trouble is, compiler optimisations will optimize away apparent syntactic dependencies. So on the left-hand program in thread 2, I have a load into the register R2, and then I use the register in this expression that I store to X, but the compiler will spot that when I add R2 and then subtract R2 from 42, that's kind of pointless, and I can just have the value 42. And then this program will be subject to the reordering that we had previously, that we explained we had to have in order for implementations to work above, like ARM processors. So this syntactic approach doesn't work. We're going to need something a little bit deeper that's more of a semantic notion of dependency. So in fact, the C++ committee collectively have understood this, that they need a semantic notion of dependency. They have these papers that they write to explain deficiencies in the language and, to try out extensions and explain them to the committee. And there's one of those which says, well, if we had a semantic dependency relation, and then we said that cycles in semantic dependency union RF were forbidden, then that would solve all our problems. We've got these two programs. The question is there a syntactic dependency between them, and is there a cycle in dependency union RF? For the left-hand program that we wanted to allow, we don't have a semantic dependency because on that right-hand thread, there's this concrete value 42, and that means we don't sort of morally have a dependency. On the right-hand thread, we do, and we wanted to forbid that. So this semantic dependency approach looks like it should work. So what we have done here is we've built, two variants of semantics. The first is a denotational semantics that avoids thin air reads and has a compositional property. So this is a bit different to the other semantics that exist for weak memory because of that compositionality. We have for this semantics data race freedom, DRF-SC, I should say, and we have a refinement relation that we can use to validate optimisations. This semantics gives us our notion of relaxed dependencies. So this is the definition I'm going to present to you. What we do with that then is we use that semantic dependency relation and combine it with the state-of-the-art C++ model, which is this RC11 model. And where they have a fixed notion of dependencies that they, where they have this PO union RF restriction, which we know is too tight, we replace that with a restriction based on our semantic dependency relation. And that turns out to be quite a good model we can observe for C++. We prove this is efficiently implementable over hardware architectures. So that's one form of validation that says this model is not too weak. Sorry, it's not too strong. The behaviors allowed by the programming language encompass all of the behaviors that the compiled code will exhibit. Then we have a data race free property for this model as well, one that matches the standard, the ISO standard on C++. And we have a tool for running this, for evaluating tests according to this model. And that's somewhat unusual for these relaxed memory models. And then we have observations that the leader in this field so far is promising, the promising semantics. But there is a problem there. They allow a sort of obscure form of thin air. Well, it's arguable whether it's thin air or a violation of single thread coherence, but we forbid this. And for every other model that provides an answer to the thin air problem, we can point to a test that we believe they shouldn't allow, that that we do allow, that we don't allow, or a violation of these implementability results that we've validated over our model. So I'm going to go into this now. Oh, I should say one more thing first. We have taken this this specification to the ISO C++ standard committee with one of these, with their formal process essentially, and presented it to them. And they're quite interested in it. They voted that they'd like to keep thinking about it and try to prepare a variant of this for possible inclusion in the standard. So we have some buy-in from them, which is quite nice. So just for context on our model, there are several prior models on solving the thin air problem. So there's this Jeffrey and Riley model, and this is based on event structures. I'm going to show you some event structures. Ours is also based on event structures. Their model very much has a fixed shape for programs. So it's not compositional in any sense. You can only deal with programs that have an init and then some parallel composition of threads. We're more flexible than that. There's the promising semantics of Kang et al. So that is an operational semantics that has a thread state and a memory state, and some cleverness where you can sort of promise a right value and then come back and justify it later. And that's what allows them to solve the thin air problem. And as I say, that's probably the most successful one of these semantics so far. So then there's the Pichon-Faribault and Sewell model that's based on event structures, and this MO model of Chakraborty and Lafayette is also based on event structures. So event structures very much one of the go-to ways to explain the behaviors that come up when you have the thin air problem. So far, the Jeffrey and Riley's model, Pichon-Faribault and Sewell's model, and the weakest MO model use event structures in a way that is a slight augmentation of how they would be used in event structure theory. So Jeffrey and Riley set up a game over them in order to explain the semantics. Pichon-Faribault, they use the event structures as essentially the state of an operational semantics. They alter the event structures. And the weakest MO model, again, is an operational semantics that builds up event structures. So I should say, yeah, each one of these has a little niggle with it, which means that it's not ideal. So Jeffrey and Riley forbids a reordering, which we want to allow, and we observe compilers doing. So the promising semantics, it permits this co-psych example, which appears to be thin air or possibly a lack of coherence. Either way, not good. The Pichon-Faribault and Sewell model is not sound over the ARM architecture, and the weakest MO, in the ESOP paper, we present a test where that seems to allow thin air behavior. So our semantics behaves better in all of this, all of these ways. And really valuably, our semantics integrates well with existing axiomatic models, so it is palatable to the C and C++ people. So let me throw the denotational semantics at you, at least in a high-level way. So what we're trying to do here is provide a denotation which explains the behavior of a component of a program. and that in a way that component can be further composed with other pieces of program, and that we can extend the denotation to explain the composition of those further components. So if we have syntax for 2 bits of program, P and Q, they may not be the same, but if their denotations are the same, we expect them to behave in the same way in an arbitrary context. So that's the lemma at the bottom. So if we have the denotations of P and Q are the same, then in any context, we expect the denotations of the contextualized component to be the same. So, as I said, we're based on event structures. We're going to build these event structures up piecewise. The way we do this is sort of back to front. That'll become apparent in a moment, but let me just start with really basic stuff. So if we have a right here of the variable R1, we have this row which goes along with the evaluation of the semantics. It's a register environment. So the semantics of this right R1 into Y becomes one of these right with value to variable Y with value row R1. A concrete right would just, is there a, oh, it's just people joining, I understand now. Okay, so a concrete value right will not bother looking up in row, it will just have the concrete right made explicit. Because my illustrations are not, have been flattened by this mode of presentation, I can't animate this. And I'd quite like to. Tell you what, can I edit this? Yeah. We're going to do an undo chain to get an animation going. Sorry for this slightly weird thing to do. All right. So I said that we're going to end up producing these event structures from the back to the front. So if we have if we're asking what is the semantics of this, this breaks down into a composition of this second part of the program. I think you can't see my mouse pointer, so I'll have to explain it. The semantics of this program, the sequence.
You can see your mouse pointer.
Oh, you can? Excellent. Yep. So this sequencing breaks down into the evaluation of the second part of the sequence composed with the first part of the sequence. And like I said, we evaluate back to front in this semantics. So the first thing we'll do when we're trying to, when we're producing the denotation of this program is get the semantics of this right of 1 to Y. And that's going to produce, as I said before, just a right event. The next thing we do is we look at the preceding event, the preceding code, and that is a read of X. So we're going to duplicate this right of Y for all possible read choices of X. So here's an explicit choice of X equals 0. That's going to be one of the choices. And we'll work here in a setting, for simplicity, where we have only 0 and 1 as possible values. So we end up with copies of this right Y beneath the read events that correspond to all value choices. And each of these basically forms a possible trace of the program. The next step for us building the semantics of this thing is to place these in conflict. So these are the essential components of an event structure at this point. You have program order. We actually add a few additional arrows, which I'll get to in a moment. And you have this conflict relation. Conflict really means you must make a choice here. So you could read 0 from X, or you could read 1 from X. Now, the way this semantics works, what we're trying to do is ultimately spot false dependencies and choose between those and true dependencies, where we want to recognize the true ones and not the false ones. This program here, there's no real dependency between the load of X and the store of Y. And it's in this construction of this conflict relation, the composition of this trace with this trace, where we spot this. And what we really look at is, well, we build something called a justification relation that explains which reads you have to see in order to have a particular right. So we have to see this read of X0 to see this right, and we have to see this read of X1 to see this right. when we do the coproduct, we check for parts of the subgraph where the same write is going to happen regardless of the read on the top. So when we coproduct these, we spot, oh, there's a write y1 here and a write y1 there. They have the same label, so it doesn't matter what read we see. There's no dependency here. So in this instance, we would actually end up getting rid of these dependency relations. Or rather, these justifications. Justifications turn into dependency relations. So this is the core idea of the semantics. Enumerate all possible forward traces through this in a sort of graph of events, essentially, and then look for symmetries where certain things are independent of the reads that we're composing at the very top. Cool. So parallel composition, just put two event structures next to each other. That's the rule for these. So we have, this is one of the programs we looked at before. And in this instance, we're using the registers R1 and R2 to link between the two, well, between the load and the store variable of the variables. And because there's a write Y0 and a write Y1 here, we don't have any equivalence of the label. So when we do that coproduct here, the justifications remain in place. We don't get rid of any dependencies. So this is the picture we'll end up with for these two programs in parallel composition. Now we can just apply the rule that we were talking about before, this acyclicity of dependency union RF, to kick out executions that we're not happy with, that have cycles. So this execution where we write one, we read it over here, and then we write one to X and read it over here. It's cyclic through these dependencies that we've left in place because they didn't get taken away in the coproduct relation, and we'll forbid this execution, which is desirable. This is a thin air execution. I do want to point out one other thing about this program. So we don't have an init in this program. So there's nowhere sensible to read x0 or read xy from. The only place we can do that for this fragment of a program is from these later writes of 0. And that has the same problem as the other, program, the execution where we read 1. It's got a cycle in DP union RF. If we were to include an initialization of 0 here, we would provide a sensible place to read x0 and read y0 from, and this would become allowed. But my point is that we have the facility to represent open programs here, not just programs that are completed, but programs that are fragments and maybe composed with some context. Okay. So I've said this already, but I do want to labor it because it's the core of the idea. And it is that when you have a coproduct being performed and there are writes that are different in the two sides of that coproduct, the dependencies from the top reads are, hold on, sorry, I have water here, which I'm going to drink. The dependencies from those reads are kept in place. When there's an equivalent write in the two following the two reads, those are made independent. So the dependencies are essentially removed here. So on thread 2, we have an independent write and no dependency. On thread 1, we maintain a dependency. In the parallel composition of these two threads, when we look at the execution where we write 1, read x1, write y1, read y1, there's no longer a cycle in dependency union RF. So this execution is now allowed, which is the desired behavior for this program. So let me present a more complicated example just to show you that that idea is relatively simple, but how you allow that idea to go forward when you compose more and more becomes quite complicated. And we want to take into account things, optimizations like load forwarding. So let me just tell you how we want this program to behave. So here, one thread, which is loading from Y into R2, And this line here says, well, if that R2 is 1, then I would like you to load from R2 again, load from Y into R2 again, and then write to X the value you loaded from R2. Otherwise, just write X equals 1. So the load forwarding optimization here would spot that you've already loaded Y once. Why not simply reuse the value R2 here? And because we've checked that that R2 must be 1, why not have the value 1 here? Now, if you have the value 1 read from Y here with a concrete value, you'll see that this entire expression just is a right of 1 to X, concrete value 1 to X. And so is this. And then there's little point in having the if statement anymore. And you've sort of destroyed the dependency between the load of Y and the right of X. So this ends up being recognized by our semantics. There's an additional rule in the semantics which helps here to get the right answer. Let me start with the bottom of this thing, which is this, what's in red, the read from Y, write to X. So here we have the read from Y, write to X part of the program. And we talked about this before. We get this, this event structure with the dependency edges recognizing the lack of symmetry between the right of X 1 and the right of X 0. So we're ultimately going to end up with an independent right of X here. This is slightly frustrating now because it's not, because it lacks the animation. Okay. So let me just delete a bunch of stuff and work with this. Apologies for this lack of slickness. So when we compose this read of Y, so that's the read of Y here, onto the event structure that corresponds to this conditionally guarded branch here, we know that we must have read 1. If we read Y1 up here, then we fall through into this conditional and it succeeds, and we end up in here. Because we do a read of Y here at the top, okay, because we do a read of Y here at the top and there's another read of Y here, our semantics recognizes the possibility for load forwarding here, and it will swap the dependency, the justification edge here from 6 to 7 to a justification edge here from 3 to 7. So this load of Y essentially supersedes the load of 6. It represents the possibility of load forwarding. Then when we come up here to the very top, we check the other possibility for this first load of Y. It could load 0. That will fall through into the else branch with a concrete right of 1 to X. That event is here. When we do this coproduct at the very top, now we recognize a symmetry between the two sides. From 1 to 2, we have a dependency, and from 3 to 7, we have a dependency. But these 2 and 7 labels match. So what ends up happening is we'll end up lifting that dependency and making these independent. So for this program, we're going to say that this right of X here in 7 is independent. Well, our semantics will say that. Now, that's the right answer, it turns out, for a very specific reason. And that's to allow an optimization observed in the Hotspot compiler of Java. So this is the optimization I talked about before, where we take this lot and it turns into this here. And then we can, in fact, even go further and reorder the X and Y because they're now independent. This optimization is performed by the Hotspot compiler, and it is disallowed by the Java memory model. So this is the, way back, this is the example which says, the Java memory model is unsound with respect to Hotspot. In our semantics, we have very different denotations for these 3 programs, but there is enough information in here to talk about the behavioral equivalence, essentially, of these things. And the point is In the paper, I don't want to go into it because it's too much for a talk like this. We have a notion of refinement, which we've proved sound, that allows us to say that these optimizations, as performed by the Java Hotspot compiler, are sound under our semantics. So what we're saying is that the behavior of the T1 here, the original code, in any context has more behaviors than T2. So it's a sound optimization to move from here to here, and likewise from here to here. So we have a definition of refinement and a proof that that refinement is sound for our memory model. And it accepts this important test. Okay, let me go on to just talk about data race freedom briefly. So we have a proof of data race freedom for this semantics. And this turns out to be a really big proof. The way we do it is we relate it to the Bowman-Advey semantics, where cycles. So this was a very early C++ semantics for that memory model there, and it has this program order union RF acyclicity. We relate our semantics to theirs and say if we're data race free, then the behavior of our semantics is a subset of the behavior of their semantics. And we show that a program that's racy in our semantics is also racy in there. So this gives us data race freedom, DRF-SC, so which is to say, if you have no races in your program, then it behaves according to sequential consistency. This is a really valuable simplification. These models turn out to be really complicated, but the expectation is that there are programmers who will write without data races and will expect sequential consistency. And this theorem serves them, essentially. And it's something that the ISO are very keen on, the International Standards Organization. So what came before was an explanation of our denotational semantics. Now I want to move to talking about using our calculation of dependency to augment the RC11 semantics. So this ends up being, that semantics before didn't deal with all of the nuances of C++. It gave you a relatively limited set of features, loads and stores, and it has locks in it. But it gives you this compositional property, and it gives you this, we have a refinement relation for it. Now we're going to take the ideas that we had for building the dependency relation there and combine it with the axiomatic model of RC11 in order to essentially fix problems that it has, where it gives the wrong semantics to thin air type litmus tests. So the nature of RC11 is you generate a set of pre-executions and then filter them according to the set of axioms. The way we intervene on standard RC11 is to generate that set of executions, the pre-executions, in our semantics that builds semantic dependency. So we build the event structures for your program. We take arbitrary read values. We don't apply any restriction to loads that you would normally do in a memory model. And then we take all of the possible traces from that by essentially resolving conflicts one way or the other. And for each trace, we have a dependency relation, which we combine with that trace. And then we just hand that to the axiomatic model. So those pre-executions that we generate are a little richer in what they include. So we're building our pre-executions. And they now have S steps with them, and the mechanism I showed you before is what builds those. Now we can just apply to each trace the RC11 memory model, but where previously RC11 would have applied a PO union RF acyclicity condition, we now use this new semantic dependency relation to apply dependency union RF acyclicity. Now this turns out to be quite a good model. It ticks a lot of the boxes for C++11. So one of the things we can show is that this is implementable. So we already know that RC11, the behavior of a program under RC11 is a superset of the behavior of a program under this IMM model. This is the intermediate memory model. I know Ori's in the audience. I think he was on that paper. So we said there's this IMM model. It's incredibly useful. What it does is it provides an intermediate notion of what the underlying architecture is going to provide in terms of guarantees. And it's this step from IMM to the hardware model. So what this says is, if you were to compile P and then run it under the semantics of the hardware model, these are the behaviors you would get. The IMM model basically says, we give you this step from an intermediate model that looks a bit like the hardware model, but is sort of much closer to the programming language model. You know that you can soundly compile to the hardware. Another step, this other step is also provided in this same paper. And what we do is we show that our model is a sound approximation of the RC11 model in the case, yeah, just that, in fact. And the intuition of this is fairly solid. They make a stronger restriction than we do, that PO union RF is acyclic, and our dependency union RF restriction is just a weaker restriction, so we allow more things. So similarly, we can provide data race freedom. So this is the data race freedom guarantee provided, well, claimed by the International Standards Organization, where if you use only atomic accesses that have SC semantics, so this is like in C++, you get to annotate your accesses of memory with a strength, essentially, and you can say, oh, well, I want it to be relaxed, and then you get a very relaxed semantics for that. It allows a lot of behaviors, but you compile to bear machine instructions. If you annotate with sequential consistent, then your accesses turn into heavily guarded little recipes with fences on the hardware. And they say if you use these very strong sequentially consistent loads and stores and have no other races over your regular accesses, then you'll be given sequential consistency. And this is a property that we validated for our semantics. And again, we lean on the same result provided under RC11, but there's a bit of work to do to match between the two. So our model has an evaluator, an automatic evaluator. I think the reason that this is unusual, because I don't think any of the other relaxed memory models that solve the thin air problem have an automatic evaluator. We believe we've kept the kind of explosion in impossible outcomes to a minimum here. So we have been able to efficiently execute our model. And that means that we've been able to just run it automatically over the whole corpus of tests in all of the papers in this field of research. And we have these in the appendix of our paper, and you can inspect them. And essentially, we provide, the right answers. So this is encouraging. It's also, I should say one other thing. It's incredibly valuable for interaction with people like the International Standards Organization to be able to have an automatic evaluator. They will not look at mathematics. I've worked with them quite a bit over time and managed to get changes in that specification, the C and C++ specifications. And we learned really early on, if you show them mathematics, they won't do anything. They want to understand it by playing with an evaluator. And this evaluator gives us that, essentially. Okay, so I'm going to conclude now. So we have a semantics here. It follows more closely the typical shape of the typical way to use event structures than, for instance, having an operational semantics that manipulates an event structure. It's modular in several senses, I guess. So in one sense, it's modular. The first version of the semantics I showed you, we can actually treat a program in a denotational way and compose the meanings of programs together to understand the meaning of the whole program. That's the first time I think that's been done for a model that solves this thin air problem. And it's also modular. The second variant is modular in the sense that what we provide there is a relation that captures semantic dependency. We combined it with this IMM model and with this RC11 model. These are just axiomatic models that happen to be really good representations of C++, so they're of interest to us. But there's no reason that you couldn't combine that semantic dependency relation with really any axiomatic model. So there's a sort of modularity there as well. We have the ability to validate compiler optimisations using the refinement relation. As I've said several times, it's possible to integrate this in a palatable way into C++. So when we wrote a suggestion for change to the standards committee, it was a page change, rather than a deleting of the, all of the tendrils of the memory model from all the way across the standard and implementing something else. So this is sort of nice in that one could see how it might actually be changed in practice in the standard. We have this automatic testing infrastructure, and for each of the other models, we have identified a little niggle which we solve with our semantics. The paper is available online, and I guess it's time for questions. Thank you very much for listening to me.
So I'm very happy, obviously, that event structures are being used, but I wonder if they're necessary. Could you replace them by the set of all interleavings of events? I hope the answer is no, but I'd like to know why.
Sure. No is the answer. Let me, if I zip back in the slides, it's probably easiest for me to explain. So the reason we're using event structures is very much to spot symmetries. Let's see. Here we go. This is a good slide. So in this code here, at the bottom in thread 2, whether we load 0 or 1 from y, we're going to see a write of 1 to x. But in thread 1, whether we load 0 or 1 from x...
Sorry, guys, I keep jumping out. Sorry.
Okay, it dictates the value we write to y. So what we're using the event structures here for is to have oversight across all of the possible traces that we might have and spot these symmetries. Does that help?
It sounds from what you just said that the same information's there in all the possible traces. It's just easier to spot using event structures. Is that fair?
I think the thing that you would lose if you have, you said interleavings, but if you had like all traces, let's say, you would lose the link between this ry0 and this ry1. These come from the same program point, essentially. And that's a valuable piece of information here.
Okay, thanks. I don't quite understand, but I'll get to. Thank you.
Simon?
Hi, Mark.
Oh, hello.
Yeah, I was wondering whether you had made any progress on the mathematical formalization of the computation of the dependency. Because last time we talked, I remember it was quite low level, let's say, the way you compute those dependencies. I was wondering if you had made any progress on trying to kind of formulating the construction of your model in a bit more abstract way.
Not yet. So one of the things, we've been pushing in a slightly different direction. I think there's one really big chunk of value here, and it's the idea that you can calculate a semantic dependency relation. We have one way of doing that, and as you point out, it's super low level, and there's probably a more elegant way of doing that. What we're really interested in doing is trying to tackle some of the other problems that come with a language like C++. So we've been looking at the semantics of pointers. So yeah, that's the answer I'm saying. Like, no, we haven't done that, but we've been going in a different direction. We've been looking at pointers.
Okay.
You could go ahead and plug in, if you had a better definition of semantic dependency, which is what we were talking about last time I talked to you, you could plug it in, essentially.
Okay. Yeah, I would be interested in reformatting your model in a little bit more abstract way.
Yeah, we end up having to do some interesting things in order to deal with pointers, actually.
Okay.
And that would probably have some bearing on the ideal sort of approach that we were talking about before, I think.
Okay.
If we don't have any further questions, then let's thank Mark again, especially for the patience with all those trolls.